think we're up and running. I don't see the wheel of death. So I guess the audio is working. Sometimes it doesn't. And this is 15, maybe a few more than 15 problems, but a little practice. And we're going to start with something that just hopefully you saw a video on yesterday. And how to take the derivative of an integral expression. And there's a real shortcut to it. It's a 10-second problem once you see the shortcut. But developing the shortcut, I think I'll take a little time here each and every day. So let's do the integration. So we're going to integrate 4m dm, and that's 2m squared. And we're going to substitute in some functions of x, sine of 2x, and x squared. And this will get you a little practice. So another way of writing big F of x is the 2 times the sine of 2x, and that is being squared. Okay, that's a correct substitution, yes. And then we're going to subtract 2. In place of m, we're going to write x squared, dropping that in, and then squaring it. And squaring does not affect the coefficient here. Okay, so we'll make sure that everybody sees that. All right, so this is a new name for f of x. So what's the derivative? The derivative of this. So this is f of x. Oh, we got to use the chain rule. So we got to do the squaring, which makes that a 4. This drops down to a 1 with respect to where you are on the x-axis, times the derivative of the sine of 2x, which is the cosine of 2x times 2. And I guess, should I put the subtraction underneath, or we'll just go to the other side of this little separation here, partition. And so now we got to do the same thing here. So we've, oh yeah, I'm on this side. So I got to do the 2 times 2, which is 4x squared, times the derivative of x squared, which is 2x. Okay, so that's taking no shortcut. That's doing the integration, dropping in the limits, and then working with the chain rule. All right, so let's condense this now. And let's just look at f of x, little f of x, right underneath it. Little f of x, right underneath it. We have 4 times the sine of 2x times the cosine of 2x times 2 times the cosine of 2x times 2 minus 4x squared times 2x. Okay, so it's always helpful, I think, to look at an original problem, to look at the answer, and see if you can see a pattern. So you should pause the video right now and look at that. Oh, I got a bad reflection on this. Okay, so let's see. Can I do something about that? I will on the next problem. I'll try to find another spot. So where is the... Okay, right there. So you're having trouble seeing that. I'll put it down lower. So f of x was the x squared sine 2x. And it was 4m dm. And that was your answer here. Okay, hopefully you can see that well enough now. And then I'll try to find a better place in the room to do this work. All right. Geez, I wonder where I could get 4 times the sine of 2x. I wonder if taking the sine of 2x and putting in place of m, geez, that seems to get that. I might try that next time. And where might I get the cosine of 2x times 2? Well, it seems to be the derivative of this upper limit. And where might I get 4x squared? Well, geez, if I dropped x squared into m here, I'd get 4x squared. Check that. And what's the derivative of x squared? Oh, 2x. Looks like there's a real shortcut to these problems. So maybe I should just do another quick one and take the shortcut. So let's say we have g of x. G of x is equal to, how about we do 2x to x to the 5th sine m dm. What's g prime? Big G of x, which could have been called little g of x. Well, I think it's drop x to the fifth then, and I get the sine of x to the fifth times 5x to the fourth minus, I guess I dropped 2x in there, the sine of 2x times 2. I guess I'm done. If I learned anything from that procedure, that lengthy procedure a moment ago, I guess it's real quick and easy to take the derivative of one of these area under a curve. The values that you're entering to that curve are definitely affected by those calculations. And so there's this chain of events with respect to rate of change. All right, so that's problem number one. And I think if I work from here on down, hopefully we're in good shape. Maybe I'll come over. Let's see. Oh, that's a lot better over here. All right. All right, next problem. I'll actually have the printout here. I'll keep that in my hand. Average rate of change. And again, if you're getting average rate of change wrong at this stage, if you don't know what to do, you better kick it in gear. So this is actually in graphing form. X minus 0 cubed minus 12 times x minus 0 and plus 0. And if you wanted to, you could. So I'm going down at 12 to 1 here at the origin. I'm going down at 12 to 1. And I've got maxes and mins. This is what the graph would look like. And we're trying to find the rate of change from here to here. So I need this x value and I need that x value. So, well, all I got to do is plug in negative 2 to 2 for x cubed minus 12x. And I get negative 8 plus 24. And here I get positive 8 minus 24. So this coordinate was 2 comma negative 16. This coordinate was negative 2 positive 16. I happen to know that those are maxes and mins because I'm very familiar with this calculation. You'd have to prove that that's what it looks like for yourself. But that's the picture that goes with it. How would you know that it looks like that? I guess you'd have to do your old y equals x cubed minus 12x. Y prime is equal to 3x squared minus 12. If you set that to 0, I think you could see that you've got a parabola that's changing signs at negative 2 to 2, positive, negative, positive. So something is increasing, decreasing, increasing. And otherwise, I don't know, maybe you throw it in a calculator for yourself. But so what's the average rate of change? So let's put these numbers in now. This was negative 16. This one was positive 16. All right, so this has changed by minus 32, and this has gone up by 4. So minus 32 divided by 4, negative 8. So the average rate of change is the slope of the secant line, and that slope is negative 8. And we can see that that's not as steep as what's happening at its point of inflection. Okay, so that's that answer. And there's the picture that goes with it. Usually I ask you where on that interval is the instantaneous. Did I ask that? Yeah, I did ask. So probably here and here. Where are we? Where are we? Probably here. Somewhere here and here. You're going down at 8 to 1. You're going down at 12 to 1 here. So where would we find those? Well, we set our instantaneous rate of change. Yes, you can see this. 3x squared minus 12. That's our instantaneous rate of 12. Instantaneous rate of change. And so when does that equal negative 8? I guess I can erase this now and work up so you can see. Add 12 makes this 4. That gives me 3x squared. So we can see that plus or minus the square root of 4/3, which is 2 over root 3, is the value C, is what they usually put in a textbook since A and B are taken. So that's what these values would be. Square root of 3 is 1.73. So a little bit to the left of negative 1 and a little bit to the right of positive 1. I've got the same rate of change as the average rate of change between those 2 points. All right, so that's that problem. We've been doing it since the start of the term. Hopefully you followed that conversation. If not, try YouTube video on mean value theorem for derivatives. So problem number 2, MVTD, it's on every test the rest of the year. If you want to keep getting it wrong, don't take that advice. All right. 3, y equals the square root of x. There's the square root of x. We're going to go from 1 to 9. I feel like I've done this problem a lot. And we're going to find the, not the average rate of change, but the average value. Now, the average value is this area. This area. And we partition it. We divide the area. And how do we get the area? We take the integral from 1 to 9 of x to the 1/2 dx. Done it so much now, I think we can probably write 2/3 x to the 3/2 x to the 3/2 from 1 to 9. Let's do a little better job with that. And then we divide that area by the width, which is 9 minus 1. And when you get area divided by width, you get a height. The height looks to be right about there. And that's what we're after. We're after this y value because the areas, this is overestimate, this is underestimate. They kind of cancel each other out, those areas. And so we take, that's the picture. That's the picture. So we're looking for this height. All right, so we do the math. We do the math. Can you see over here? Yes. Square root of 9, 3, 27, 9, 18. I feel like I can almost memorize this one as well. Minus 2/3 divided by 8. Okay, so we got 54 minus 2, 52 divided by 3 divided by 8 is 52 divided by 24. 52 divided by 24 is 26 over 12, which is 13 over 6. So a little bit bigger than 2. All right, so if I had a very good graph, I had a very nice graph of this, and if I didn't make any errors, then a little bit bigger than 2, 9 would probably be out here now. Okay, so a little bit bigger than 2 would be about here. That doesn't look good at all. So I hope my math was right on that because I did it pretty quickly. But the average value theorem, again, from A to B, fx dx divided by b minus a. If I did that too quickly and made a little math error, well, we'll correct it in class tomorrow. All right. That's the average value of a function. The area under the function from A to B divided by b minus a. All right. Let's see what's next. All right, we're integrating x squared plus 11 to the 19 dx. We're going to use u substitution to do this. If you got a good handle on u substitution already, you should try to do this one in your head. I always like practicing that. So I'm going to do x squared plus 11 to the 20. I know I'm going to divide by 20. There should be a 2 here. There isn't a 2 here, so it's got to be 1/2 of this plus c. And let's see if we can get that same answer using u substitution now, because you haven't got as much experience as I have. So let's find out if I get too old to do this anymore. So let's let u equal x squared plus 11. So therefore du is 2x equal to dx. There we go. There's our 2 substitution statements. So here I have x, here I have u to the 19, here I have du over 2x. So yes, I can pull a 1/2 out. The x's cancel. This is 1/2 u to the 20 over 20 plus c. And so that's 1/40 x squared plus 1 to the 20th plus c. And I believe that's what we had before. Okay, now, one thing we have also practiced or are going to practice a lot is changing the limits of integration. So let's just say I threw a 2 and a 3 in here. Now that's an actual number. So I have to come over here and I got to do a 2 to a 3. If I throw a 3 in, I get 9 plus 11. So that becomes a 20. This becomes a u du problem, right? And where am I? I'll throw a 2 in. That becomes a 15. And I guess I should have shown that the 2 comes outside. Maybe you can intuitively see that. All right, because those x's would have canceled and I would have pulled the constant out. So that's going to be a problem on your test as well. You don't have to do this out. You don't have to do it out. We'll do that. We'll do some definite integrals somewhere else on a test and make sure you can do the mathematics. All right, you write cosine using an integral expression. Well, if I'm going to write the cosine of x, the parent function, then I need its derivative, which is the minus sine x. I'm still dry. Still got that. Looks like maybe I think it's from the light above here, but all right, so I can work to the right now. So minus sine x is that first shape, and we're going to go from 0. Okay, so we're going to accumulate this area under this curve. That's negative area, so it's going down in a concave down, concave up fashion, and then it's going to come back to 0 in a concave up, concave down. So there's your cosine curve. All right, so what's it coming from? It's integrating minus sine x dx, right? Gives us the general shape. But we got to realize that cosine of x at 0 is 1. Cosine of x at 0. So if I pick 0 here, and I'll make this a dummy variable, I'll use m dm, and I'll put x there. That's going to turn it into a function of x. That's going to be big F. It's going to be my, when I integrate minus sine x, I get cosine m. When I integrate minus sine m, I get cosine m from what to what? From 0 to x. And that gives me the cosine of x, which is what I wanted, minus the cosine of 0. That's a problem, all right? Because when I let x equal 0, I'm not getting this function anymore. I'm really getting cosine x minus 1. So how can I rectify that? How can I get that minus 1? Well, I get the marker. I got the marker. I guess I can just do this. And I guess that means that I want minus 1 plus this is my new big F. Right? So that's that problem. That might take you a while to see pictorially, but we keep doing it every day, trying our hardest here. Okay, so big F of x is equal to minus x cubed. Geez, that's something that changes sign at 0. Times 4x minus 8 squared. Geez, that has a root of 2, but it doesn't change signs there. And x plus 2. Oh, that's a linear root. That's going to change signs there. And I want to know, well, I guess this was little f of x, huh? This was little f of x. And I want to know when big F is increasing. When is big F of x going up? Well, I guess whenever its slopes of its tangent lines are positive. Well, I guess if I draw a tangent to a curve, got a slope that's positive, I guess that means the y values of that curve are increasing. So I guess, derivatives, they find the slopes of tangents to a curve. I guess I want to know when they're positive. Well, let me put a number bigger than 2 in here. Let's put 1,000,000 in here. Well, that's negative. 1,000,000 squared, that's positive. 1,000,000 plus 2 is positive. It looks like I get a negative result when I get a number bigger than 2. So I guess it looks like this. Guess that's what the curve looks like. Geez, when am I positive? Oh, goodness, sure, these y's don't look positive. No. All these y values look like they're positive. I guess between -2 and 0. That's the interval where big F is increasing. Yep. All right, next problem. Find the first quadrant area bounded by y equals square root of x and y equals 3 in terms of x. Square root of x, so let's get a little picture here. Square root of x, here's y equals 3. Here's the square root of x. Oh yes, it intersects at 9, 3. And it looks like we have 0, 0 over here. And I guess this is where it's bounded because square root of x can't be less than 0. First quadrant area bounded by those two. Yeah, well, it's the only bounded area anyway. So we want this bounded. Oh, geez, that's a rectangle. It's got a height. It's got a width. Let me see if I can define that height. That height. Oh, see, this is a height of 3. And I guess that's an x value. And I guess that height of 3. Geez, this particular one here doesn't look like it's 3. Well, it looks like I have to subtract this. And how do I get that x value? Oh, that's right. It's the square root of this. So 3 minus the square root of x gets me this rectangle. And I guess that's a different square root height because that x is different than that one. Why don't I integrate this from 0 to 9? And do all those rectangles all the way across. And let's see what I get. Oh, I got to get the widths in. The widths are dx. So that's 3x minus the square root of x. We've done that so much here. 2/3 x to the 3/2 from 1 to 9. Okay, I guess we should do it. 3 times 9 is 27 minus square root of 9. Oh, we've done that so many times. That's 18, isn't it? I believe. Oh, wait a minute. Maybe let's check. 27. Yeah, that's 18. Yeah, I thought we'd done that so much. Minus, let's drop a 3 in here. That's 3 minus 2/3. That's not too bad. 27 minus 18 is 9. 9 minus 3 is 6. 6 plus 2/3. Okay, wasn't too bad. Right here. That's that area right there. All right. I keep dropping these erasers. I wonder if I'm making any careless errors. If this was my test, I think I'd probably take a little more time with it. But I'm not grading myself. Let's see. Oh, same area, but in terms of y. Oh, I wonder how we do that. In terms of y. So that means I'm adding up all these x distances. I'm going to add all those x distances until I get to a height of 3. And I'm going to do that from 0 to 3. I wonder how I can get those x distances for y equals square root of x. I wonder what x equals. Oh, yeah, y squared. Yeah, I don't need the bottom part. Y squared. From what to what? 0 to 3. So I can go from 0 to 3. Those x distances come from squaring the y values. So what does that give me? That gives me y to the 3 over 3 from 0 to 3. 27 divided by 3 is 9. That's not what I got the last time. I'm going to go back and do that other one again. Because now I've done it from two different connections, 2 different perspectives. And I think I made a math error. Oh, it was 1 to 9, wasn't it? Am I doing the wrong problem here? Bounded by, did I think, you know what? I think I did 1 to 9 because that was an earlier problem. And the old guy's getting real old. So let's go and do it real quick. From 0. So that's 9. That's 3. So integrate 3 minus x to the 1/2 dx from 0 to 3 to 9. I bet you anything I did that. So this is 3x minus 2/3 x to the 3/2 from 0 to 9. 3 times 9, 27. Drop in the 9, and we get 18. And that would have been 0. So yeah, there's your 27 minus 18. There's your same answer we got when doing it with y. So I think I reverted to a little poor muscle memory from problem number 3 earlier. Yeah. Okay, so they are the same, and it looked like it was easier to do it in terms of y. Okay, I'm not going to make the video over again. just going to continue on. That's the beauty of doing things from two different perspectives. That's how you check. That's a big, important aspect of doing mathematics. Trying to get an answer from two different methodologies. All right, use limits to depict the instantaneous rate of change of x squared. Okay, so there's two ways to do it. We're going to look at rate of change. If you want rate of change, then you better get something here and you better get something there. That's how we measure rate of change. The change in the outputs divided by the change in the inputs. Okay, miles per hour, all kinds of gallons per dollar, whatever. So what do we do? Well, there's two different ways to do this. And I'd like you to be able to understand both of them before the end of the term. So pause the video and give it a shot. All right, so if I wanted this one, then I let x squared, that's my second x, my second y. And I say, okay, what makes it a derivative? They have to be close. They have to be close. Well, how can I make them close? I say the limit as x goes to 5. Of what? The change in y over the change in x. That's the derivative of x squared, which is 2x. And what do I do when I put a 5 in? That equals 10. Now I said do it algebraically. So how do you do this algebraically? Well, you would have factored. You would have done x minus 5 times x plus 5. Right? What happens? The x minus 5s divide out of the problem. Now I can substitute 5 in and I get 10. So that's one algebraic method. Okay. Now we're going to do it again. But we're not going to write the derivative from that perspective. We're going to write it from another limit perspective. What would that be? Well, 5 plus h, where h is kind of like run, the change in x to the right. We're biased. It's easier to do it that way. And so what do I get? I get 5 plus h squared. And when will this be a dx? When will it be a small change? When h goes to 0. I have what? I got 5 plus h squared minus 25. If I subtract 5 plus h minus 5, I think we can see we get h. Guess what this answer is going to be? If you guessed 10, you would be right. So let's do it out. 5 plus h squared, let's do it out. 5 plus h squared is 25. 5 plus h, just as a reminder to my class from last year, and maybe something new here. You double the product, so that's 10h. And you square h, and then you subtract 25, and that's the change on the right side of the table. The 25s cancel. You divide h into both because this is the same thing as saying 1 over h times 10h plus h squared. I don't know why we don't have a distributive property of multiplication. Distributive property of division might be nice. I know it's the same as distributive property of multiplication, but it might be nice at the younger age to actually say it and write it that way so that people don't make mistakes like 4 plus 2 divided by 4 is 2. Because you see it algebraically all the time, people making that statement, which is obviously not correct. All right, so what do we get here? H goes into h, that cancels. H goes into h squared to h. I've divided h out. Can I let h go to 0 now? Yes, I can. And I get 10. Yeah, don't worry. I'm going to give you an opportunity to write those limits the rest of the semester on every test. So don't feel bad if you didn't get it. You're going to get lots of more opportunities too. Right. Find the derivatives of the following. These are just pure practice. So I'm going to put big F here, little f here. Well, I'm going to change the notation. I don't want you to think that that's always the notation we use. I'm going to use little f and f prime. Okay, so I'm just going to do them out. So sine cubed x to the 5th. And even though you know how to do these, you should still practice them. I don't think the NBA players who are hitting good three-point shots all of a sudden stop. I think they're out there every day doing what they know how to do and they're getting better at it. All right, so we got 3 sine squared. That takes care of the cubing of what? X to the 5th times the derivative sign, which is cosine of x to the 5th times 5x to the 4th. Okay, again, YouTube chain rule problems if you want to get better at the mechanics of that. Next one. Square root of cosine x. Derivative. Derivative of what's inside. Derivative of cosine x is minus sine x over 2 times the square root of what's inside. I've asked you to memorize that form. Square root sine 2x. You got another chance at it right now. How do you get it? Derivative of what's inside, which is cosine 2x times 2. I'm going to start putting the 2 in front. Start saying it that way from now on. 2 cosine 2x divided by 2 times the what's inside, sine of 2x. Obviously, you could simplify that, but that's the mechanics. ln of 5x cubed follows a similar pattern. Derivative of what's inside, which is 15x squared, over what's inside, 5x cubed. Now, let's simplify that to 3 over x. And let's use our rules of logs to see where that comes from. Okay, hopefully you get enough time with that. So what's another way of writing this? The ln of 5 plus the ln of x cubed. What's another way of writing that? The ln of 5 plus 3 times the ln of x. Those are your log rules. Derivative of a constant is 0. Derivative of ln of x is 1 over x times 3. Then we get 3 over x, which is what we said a moment ago. Square root of f of x. Give you a chance to get away from that. Coming right back to it. What's the derivative of the square root of f of x? F prime of x over 2 times f of x. Square root of f of x. There's your derivative. All right, what's the limit? As x goes to infinity. X minus 8, x minus 2, 1. And I mean, if you put really, really big numbers in, these are the same exponent. So it's a over b. When they're the same, it's a over b. And in this case, it's 1 divided by 1, which is 1. The limit as x goes to infinity, 6x minus 2 over 2x squared plus 7. All right, so let's look at the exponents. The little guys don't matter. When you're going to infinity, numbers like 2 and 7 drop out. And if I simplify this, I get 3 over x. So what happens as x's get bigger and bigger and bigger? Your fraction gets smaller and smaller and smaller. Okay? All right. Getting there. Good. Gonna get home by 3. X squared minus 2x. And I'm going to put a dot here. Minus 2x times y squared, just so we can see we got a product rule here. Plus y cubed equals 12. Take the derivative. So we got 2x dx. Dx's drop out. Minus 2 dx divided by dx. It drops out. So I did the first. And there's the second. Okay, so now I got a subtraction of both parts. So I got to do y squared, which is 2y times minus 2x. So I'm going to do the 2 times 2 right here. Minus 4. That doesn't change, but y goes down 1. I'm going to write the 1. No, I'm not, because it's too complicated with respect to y prime. Looks too much the same. And what do I get here? 3y squared y prime equals 0. Constants don't change. So what is y prime? 2x goes the other side as minus. That goes the other side as a plus. Multiplication by minus 4xy becomes division by minus 4xy. Multiplication by positive 3y squared becomes division by 3y squared. And if I had an x and a y value, I could tell you at what rate that curve was changing at that coordinate. Okay. Little quotient rule here. Just trying to keep these rules in front of us every day so that you have them in your pocket. There's no chain rule here. Every single person in this class should be able to do this by this stage of the term. If not, you have some serious work ahead of you. Okay? That means you have not memorized this. You have not spent any time trying to memorize it. That means bad. All right, so what's f of x? Low, d high. I guess I don't need the parentheses. Low, d high, minus high, d low, all over a low, low. Okay, hopefully that was real simple for everybody in the class. Find the values of the local max and min for y equals, last problem here, x cubed plus 3x squared minus 24x plus 1. So what does this critter look like? We'll get some work with it. Let's see, let's keep a picture of it down here. So minus 24x plus 1 means it's going down pretty steeply right here. Going down pretty steeply. It definitely going up there, going down here, and we'll fill in the rest as we do the calculus. Be fun to put this one in graphing form because it's pretty easy to put it in graphing form. So minus b over 3a is minus 3 over 3 minus 3 over 3 negative 1. So we're going to get a point of inflection at negative 1, but we'll find it from our calculus rather than our pre-calculus method. Now, if you want to learn how to put these in graphing form, you got to go to the YouTube channel and spend some time with it. It's about 20-30 minute video, but you can learn how to do that. Okay, so y prime. 3x squared plus 6x minus 24. We're going to set that to 0. Find our max and min candidates. Y double prime, 6x plus 6. We're going to set that to 0. Now we know we get a point of inflection at negative 1. So we got to put negative 1 in here to find that coordinate. So negative 1 gets us minus 1 plus 3 minus 24. No, plus 24, excuse me, plus 1. All right, so that's 2, 25, 27. So negative 1, we're going to call that the point of inflection. So we're going to have something that does this. Good enough, good enough. And that's negative 127. So we got to find the local max here. So the local max is when this thing equals 0. So we'll divide by 3, and we have x squared plus 2x minus 8 equals 0. So we've got an x plus 4, x minus 2. Okay, so that's going to be 2. This is going to be negative 4. And the way we can see that it's concave down is to plug negative 4 into y double prime. So y double prime at negative 4 is minus 24 plus 6, which is minus 18. That's negative. So I'm on a concave down interval. I've proven that this is a local max. I got to put negative 4 in here. So negative 4 in here should get me a 2-to-1 ratio. Let's see if it gets a 2-to-1 ratio. Negative 4, negative 64, negative 4 squared, no, 48. So I had a little bit of a thought there. It certainly gets me the 2-to-1 ratio there. Negative 64 plus 48. Minus 96, so that's positive 96 plus 1. And that's going to be negative 16 plus 1, negative 15. Go down 15. And we're at 81, I believe. I believe that is the local max. And this was, what the heck was this number? Save me some time. God, 27, I think, right? So how far is it from 27 to 81? Oh, that's a 3-to-1 ratio, isn't it? Yeah, that's really nice. I think about that some more. Seems to be a nice little pattern there. So if I've gone up 54 units and I got to go down 54, I think that's going to be negative 27. Somebody do it out and let me know tomorrow in class if that's true, because I'm running late here. I got to be somewhere else. And could be some interesting little tidbits of patterns there. We'll have to keep an eye out for that. Okay, where am I at here? I'm at saying goodbye. All right, so this should be our third day back, remote learning. Bye-bye.